Thank you everyone for attending. We have two visitors from the NextEnergy facility in Detroit. I first interacted with NextEnergy at Wayne State University when I was doing graduate work on biofuels. And they have a very broad mandate around green energy and transportation. And today we're emphasizing hydrogen and different versions of hydrogen, such as ammonia. I want to thank you for your attendance. I would like to include an observation that there is real interest internationally and here within the US around hydrogen fueled systems for both energy and transportation. So Lauren and Eric, please take it from here.
All right. Well, good morning, everybody, or afternoon. So if you're not familiar with NextEnergy, we're a group of scientists, engineers, urban planners, and we tackle the very issues that you heard, whether it's clean fuels, electrification, and that. But we're kind of a bridge, if you will, bridge between what I'll call traditional industry, startups, and government and local municipalities. And what that allows us to do is, if a technology or a product is far enough along in its commercialization pathway and you want to test it out in the wild, we're a good group of people to call to see if we can maybe find a community that would like to try it out. So just a kind of a item of that. My background, I wasn't fortunate enough to go to Michigan State. I had to go to Michigan Tech way up north, which makes this day seem almost balmy. But I will say that, my background's kind of eclectic. I've spent some time in the utility industry, oil gas industry, and then I spent last 20 years of my career working on mobility, specifically low carbon, no carbon options, and with the goal that, to get to a more sustainable future. That being the case, I've kind of lived a secret life because my original degree was actually in geological engineering, which I'll highlight a little bit at the end. But to all you in the engineering curriculum, if you get a good education, you can do anything you want, right? So let's kind of get the ball rolling after Lauren introduces herself and
Perfect. Hi, everyone. Lauren Mattar. I focus on mobility at NextEnergy. My background was also in engineering. I went to Ohio State. I grew up in Ohio. I studied industrial engineering there, and then I got my master's degree in engineering management as well. Prior to joining NextEnergy, I worked more on the continuous improvement manufacturing side of things, really kind of that true industrial engineering focus, right? So I worked in a couple of different manufacturing plants in various industries, and then just had a personal interest in green energy and looking at more cleaner projects, right? I just have this distinct memory. Someone asked me this last week. I was in a door manufacturing plant, like this kind of door, to your house or your office or whatever. And they're wrapping every single door in plastic. And I was just like, what are we doing here? This is crazy. So found NextEnergy, again, nonprofit with a mission focused on those cleaner technologies, and thought that would be a good match for my personal interest and then also my engineering background. I'm newer to the hydrogen world. I started that when I started at NextEnergy 4 years ago. So many people here probably have a lot more experience than me. Eric's got way more experience than me, but happy to share what I've learned. And especially I've got a kind of specific project that I'm going to highlight here with you all today about heavy duty refueling and some of the work that we're doing in that and some research we've been doing with the National Renewable Energy Lab. So excited to share about that, but I'm going to let Eric take over the beginning part of this and we'll go from there. Thanks for having us. I'm going to sit down.
All right. So, anybody that's in hydrogen, and don't let Lauren fool you, she's a pro. I've been on the conference call. She knows more than anybody I know on heavy duty refueling. And I will tell you that, over the last year, if you will, I mean, it's been kind of a tough haul. You know, the hydrogen hubs, a lot of them are canceled. You have some major OEMs announcing that they're going to back burner their programs. Uh, you know, if you look at that, it's like, why are we even in the room today, right? But the good news is that I've seen this before at least, and I've been there before. Okay, I was part of the original hydrogen highway back in the early 2000s with the California Fuel Cell Partnership. We watched it, with it's kind of a if you build it, they will come mantra. So it was, you know, we watched it go and then it went away. But where did it go? Hydrogen didn't go away. It's actually managed to survive quite well, but it went to material handling and heavy duty applications. Okay, where the use case didn't require any government incentive, basically. Hydrogen fuel cell forklifts, those two that walked away from it for passenger vehicles or their heavy duty applications, they have it in their plants. That's how they move their materials around. One of the largest users of fuel cell forklifts is Amazon. Okay, so um, it's pivot time again. Instead of being green, low carbon, no carbon, the mantra is energy resilience, energy you can create within your own borders, those kind of things. But that's fine. So let's get the glass half full. All right. Now, anybody that's played with hydrogen, or I'll say, alternative fuels of bio nature, any of that, everything in black there, none of that's changed. Whether you're focusing on low carbon, no carbon sustainability solutions, that's energy resilience now. Let's rebrand it. Okay. It's a domestic source. That's why countries that don't have any oil or gas, like Japan, really focus on hydrogen, right? There's numerous production pathways, and we'll talk about an exciting new one later in the presentation. It's very favorable for heavy duty and material handling use cases. Lauren's going to talk about, Class 8 truck refueling. That's where batteries start failing out because the mass of the battery competes for the functionality of the vehicle. And whether it's hydrogen ice or it's fuel cells, it's a mature technology. First time I played with this stuff, we had a situation, weather like today. And I don't know if you remember the Silver Dome, but we had a big thing in Silver Dome. The heat went out, and we had 3 fuel cell vehicles there, and we had to get space heaters so that they didn't freeze. That doesn't happen anymore. The technology is mature. You can take them out in this kind of weather. But there are some new exciting things going on. One of them is from the lessons learned from California, which did some great work, by the way. Let's not beat them up. They did some great work. But there's a partnership, a gang of four, if you will, in the city of Detroit with the city of Detroit that have created hydrogen ecosystem coalition, and we'll go into what that looks like and what it comprises. And then, the real exciting thing is this geologic hydrogen. Now, I will tell you, it's kind of weird to be at this point in my career and watch my bachelor's degree come back into play with geological engineering, but some of the stuff I've heard with geological hydrogen is very optimistic. But there's a lot of smart people in this room, in this university, and within the state of Michigan that I think are going to be needed to apply those resources to taking a look and seeing what we can do here, because there's some very favorable indications for Michigan. So if we can get that video going, it just kind of highlights, it's on the city of Detroit logo. There we go. So this was announced in August at the MOVE conference. So Biotech, Forvia, Ives, and Symbio. That's about as snazzy as we get right there.
The next one.
Yeah. So, what do these partners bring to the table? Well, Symbio does upfits of existing applications and turns them into fuel cell applications. Okay, so whether it's Class 8 trucks, city buses, garbage trucks, or even tugboats, they can convert them to either fuel cell or hydrogen ice. All right. Ivy's they're going to be doing the dispensing at 300 and 700 bar. And then Biotech is going to be doing generation. All right. And go ahead, next one. So the idea is make Detroit the center hub here. And what they're doing right now is they're going through and they call it a demand-a-thon, where they're looking for uptake. So whether it's a fuel cell cab fleet or backup power to a facility or perhaps a marine application like at the Detroit Port Authority, they're going through and they're aggregating all this demand with the idea that if they can get to roughly 4 tons today, they can get a very affordable and a contract guaranteed price for hydrogen. If you know, the less hydrogen you make, the more expensive it gets, right? So that's their goal here. And they're trying to do this, I'll say all at once, but it won't happen all at once, but they're trying to bring all these things together basically at once. Why is that? It's because if you do them sequentially, it tends to fail. We've seen that before. One of our other contracts that NextEnergy has is with the Detroit Port Authority. They have 2 EPA grants. One is for zero emission equipment. Now, most of that is going to be electric because when they wrote the grant, that's what was available for them to put on order. But as part of the planning grant, the $3 million planning grant, we are looking at select pieces of equipment. Actually, I shouldn't even say equipment. We are looking at use cases that favor hydrogen. All right. And we're going to identify at least 3 of them. And those use cases will go forward with a deployment plan. We're actually going to try and avoid the word pilot because the customers of this are going to expect it to perform as well as their diesel replacement that they're taking over from. But it's got a couple of cool aspects on it. It has this shore power barge. And, for those of you that are talking about ammonia and methanol, there are people looking at that for different fuel sources. The amount of shore power that one of these freighters use is significant in the megawatt range. So that's going to be a cool project. And then we also have a tugboat that we're looking at as maybe a serial hybrid application. So and then there's large material handling. Forklifts on a Port Authority terminal are not like the forklifts at Amazon. I mean, these things are picking up cargo containers, so they're pretty big. Now, I love this graphic. This is what happens when you ask AI to give you a graphic of geological hydrogen. All right. It's really this simple. We just got to find the bubble, right? But we all know, sadly, I know, that that's not the case. But when you talk to a lot of people who are, well, I'll say, have gold fever mentality right now with geologic hydrogen, that's the kind of dialogue that I hear a lot. I'm not saying everybody, but I've heard, I hear people wildcat and they don't even know that like a well can cost up to 50 to 100 million, So you probably want to do a little front end work before you start drilling holes. So next one. So, a little bit more technical since we're in the College of Engineering. To get geologic hydrogen, you need this and this, or one or the other or both. And then you need this. So what did I just say? Radiolysis and serpentization. So this one's converting minerals and water and turning it into hydrogen. This one is splitting water with radioactive isotopes. And those are typically deep formation, iron rich, they call them mafic or ultramafic mineralogy, like olivine, pyroxenes and that's the minerals. But so what if you're generating it? If it isn't captured, and anybody knows anything about hydrogen, it's a diatomic molecule. It's the most abundant thing in the universe, but it doesn't like hanging around each other. You either got to bully it with pressure or trick it with chemistry, right? So what you need is a confining space. You need a porous material to capture it and a confining space on top. And then you see the little pore space hydrogen in orange there. And you go, well, boy, that's a lot of things to line up all at once. Because if you're missing any one of those, none of it works. The hydrogen just dissipates. And then you can also have uptake by biological organisms and that, which you'll have anyways, no matter what. You have that with natural gas too. But, you need to be able to accumulate it in sufficient quantity to make it economically feasible.
Do we have a 17 in Michigan?
Yeah.
Yeah. What kind of a scale of reservation?
We'll go into that.
Okay.
Yeah. You're asking all the good questions. But these rocks right here, if you look at the little cartoon, surface, little trees, way down deep. Now, these do actually outcrop up on the Keweenaw Peninsula in the Upper Peninsula. Okay. About 1.1 billion years ago, there was an intercontinental rift where the North American continent started ripping apart. And so you had all these basaltic flows. Basalt is just a iron-rich lava, okay? You had all these basaltic iron flows, but you had a lot of ultramafics all come to the surface. So if you look at where people are looking for geologic hydrogen, a lot of them are following that rift structure all the way down to Kansas. It was a big rift, okay? A little bit north of the Keweenaw, all the way down to Kansas. About 1.1 billion years ago, so don't worry about it today, all right? This one over here, this is Mali, Africa. It's a field where they accidentally discovered it when they were trying to do a deep water well. It's roughly 95% plus hydrogen on a purity level, which is pretty good to start. They're using it in a very simple, like a heating power scenario, nothing too fancy, but it is a producing reservoir. All right. And this is something that they believe is in other parts of the world. Like a lot of other parts. All right. So you can see some of our favorites, Kansas, Iowa, and this intercontinental rift. It starts a little bit above here and goes right down here. This is another deal. But if you look at this, there's some interesting work. You have the Mali, Africa site down here. It's also interesting that hydrogen tends, it's not going to be pure coming out of the ground, just like natural gas is. Anybody that's been involved with development of natural gas when you get out of the ground here, just north of here in the Antrim plate around Gaylord, it comes out of the well, goes to CFP, a central processing facility where they knock out the CO2 and the water and any kind of salts and sulfides. So why do they do that? Because pipelines don't like that, right? You get carbonic acid with CO2 and you get step corrosion and all this stuff. So even that has its own infrastructure challenges, but guess what? Scientists and engineers, we learn how to mitigate risk and take care of that. So this is gold fever mentality right now. You have people with billions looking for trillions. That is as simple as I can say it. Okay.
So many of these have helium as an impurity, and helium can be quite valuable as well. What
More valuable.
What is the determinant that you know?
How do you know if you're going to get helium or not?
And what causes it? What's the underlying cause?
I'm going to give you a real honest answer. I don't know.
Okay. And do we know helium-3 versus helium-4? Because helium-3 is worth lots. Way more than hydrogen, by the way.
No, but it speaks to how we economically develop, how we develop these, what are going to be the economics behind it. Because even if it was just hydrogen, the amount of hydrogen that they're talking about is insane. But there's a lot of talk. There's really one, maybe two fields that are producing. So there's a lot of opportunity. Now, before we show the next map, this is what's causing the gold rush, the white hydrogen or gold hydrogen, if you will. Look at Michigan. So a couple years ago, the USGS published this map. All right. And, you know, prospectivity. So that means where you should look on a drill here map. And if you actually read the report, it says that this is not a drill here map. However, if you talk to people, you know, they're like going, well, we're going to drill right there and we're going to do this. And we might, but, you know, this is exciting. So why did this get out of the rest of the United States? Matt, but can we kind of see this little line right there? It's following that intercontinental rift. But this is the thing. A lot of the state of Michigan's looking really good right now. Now, what do we need to do? Next slide, please. So, to your question, and to your question, there needs to be a lot more work done. All right. What we have, and the USGS did a very good job of aggregating data from multiple sources to come up with the maps that we just showed. However, those are the first step. What we need now is more detailed geophysics, remote sensing. There's people that are looking at old wells. There's the names escape me, but there's somebody at Michigan State that's looking at the organisms that eat hydrogen as maybe an indicator of something going on down below. And all these things have to come into play. And the reason I'm showing this is because this is what needs, in our opinion, something like this needs to happen for us to realize or prove out the potential of geologic hydrogen in the state of Michigan. So, you know, the demand today is, I'll say, on the low end, right? Hydrogen storage, you know, you have the ammonia people, you have the moth people, you have the compressed gas people. You got a bunch of people all looking at hydrogen storage solutions. And, you know, we talked about it in the conversation just as people are filling in, but we got to kind of avoid this or that mentality. It's probably going to be an eclectic group. What was your phrase?
The future is not electric for transportation. It's eclectic.
Yeah, there you go. Yeah, I like that. You gotta steal.
You gotta say it into the mic.
Yeah.
Repeat it. Yeah, you gotta repeat
Okay,
it for
so,
online.
so the future's not electric, it's eclectic, right? Yeah. And, but it's what we've been preaching. It's basically, I've heard people getting arguments over fuel cells versus batteries versus ice and all that. At the end of the day, the use case and the economics determines what's gonna live. But if you get hydrogen, geologic hydrogen, at a very low cost, you enable so many more uses for it. Because when hydrogen's very expensive and hard to get a hold of, because there's not many stations, there's not that many places doing electrolysis. I think Bosch is going to bring one online pretty soon. What you don't want to do is use the most expensive fuel that's hardest to find in the least efficient way, right? I mean, if I say that out loud, that you go, yeah, that sounds like a bad idea. But that's why this is so exciting, because then you take 10 to 15 to $20 kilogram hydrogen, and you know that Mali site in Africa, they're getting it out at 50 cents a kilogram. That's insane. Okay, now that's not purified, that's not transported, that's not any of those things. So you mentioned it earlier. What happens when you find hydrogen? Well, wherever you find this hydrogen, my guess is you're going to end up with something like a hydrogen city. All industries that could use or should use hydrogen will want to be close to it, because then you mitigate the cost of storage and transportation. All right. And, you know, for us to accomplish this, you know, we need the academia folks and the industry folks focused on hydrogen storage, hydrogen transportation. You gotta get the finance crew, so the business school is going to have to get involved on hydrogen sales and brokerage. Once you start producing enough of a material, then you can create a market for it and a marketplace for it. Just like you got Brent crude, you look at that and it's $62 a barrel today. Okay, that should be the future of hydrogen if geologic hydrogen is real.
What percentage hydrogen do you expect geological hydrogen to create?
Well, if you look at that other map, it varies. The producing well that they have now, the early wells were like in the 98% range, and in the more recent one, I think, was in the 95% range.
The reason I asked is our jet fired engine will halfway burn 50%.
That's a huge plus up on the ice, right? Because you know, when you have PEMs, they can get poisoned by carbon monoxide or sulfides, right?
It turns out on the map that was shown earlier, Finland had about a 50-50 mix of hydrogen and helium, which was the most extreme one that I noticed.
Yeah.
Probably back to
And
that.
the cost per kilogram for just crude oil.
From.
Is it 50 cents per kilogram, or is there just oil out of the ground? Just well, yeah, I'm gonna compare what the ridiculous grade. I mean,
I don't know. Whoever has a calculator, do it.
I mean, how much overhead they put it in the cost. It's serious. Okay.
Well, what is a 50-gallon barrel of oil? 42-gallon barrel of oil weigh? What's that barrel of oil? Is 42.
Yeah, okay, anyway.
But I mean, come on, you're asking me to do math and engineering.
Well, I'm gonna get.
Jeez.
Take it out, just see if they're wrong.
This is a tough crowd, I'm telling you. You know, but so let's kind of ABC 1, 2, 3 this. What needs to happen is probably something like this. Near term, we should be looking at remote sensing, all the cheap stuff it takes to take that big, beautiful blue map of Michigan that says, hey, this state looks really attractive because of mineralogy, geologic structures, and some other incidental information. How do we take that whole big map and get it down to, we should drill a hole here, man? Okay. So that's kind of like really between phase 1 and phase 2. Some more exploration, geophysics, and then maybe some pilot wells. And then if we're lucky enough where one of those wells hits hydrogen, then you can start looking at what kind of modeling on the reservoir you should be doing. And, you know, even though that they have a lot of people out there looking for hydrogen, there's going to be a lot of differences with these dozen or so efforts than the thousands of efforts that have been done with natural gas. So natural gas is a good proxy for understanding the process, but there's going to be some big differences because if you're familiar with just the size of the molecules, you know, methane is kind of like Spartan Stadium, and hydrogen is kind of like the car parked outside of it. It's going to behave differently. It's going to be more diffusive. It's going to be harder to trap. There's a lot of other things to do it. But that's where, to me, where universities can step in. And then, you know, if we put on the high beams, look further down the road, and we do have enough hydrogen and we can go into production, you know, then you have commercial scale extraction. And when you get into that thing, you're in the billions of dollars, by the way. That's what it costs to bring a oil gas field to market. Because it's not just drilling the hole. You got to plumb them all together, put it to a process facility, scrub it, clean it, and then store it or send it in a pipeline. And while that some of that infrastructure exists for natural gas, there's really outside some of the southern port states, there's not really much for hydrogen. And then, you know, if all goes well, and somebody can't remember who I was talking on the phone to Michigan State, but they mentioned being the Saudi Arabia of hydrogen. That was you.
How do the oil companies miss hydrogen for 150 years in Michigan? I mean, there must be natural gas wells all over the state. Is the certificate different requirement wise? Or
Well, first of all,
right? They are enrolled.
remember when everybody was saying, what are we going to do with lithium? It's only in China and South America. That's not true.
That's for sure.
Yeah. So how do they miss it?
Well, they weren't looking for it. I mean,
They weren't looking for it.
No, that's
Where-
so in
where-
in case of lithium, there are actually a lot of known deposits that they've declined to produce because of the environmental impact. So there are, you know, huge deposits around Minnesota, for example, that they're declining to produce, and
Yeah.
the state is fighting.
Well, I can tell you, for instance, Alberta, Canada is going great guns on. But to your point, it's basically that they haven't really looked for it, or it was a nuisance. You got to remember, natural gas was a nuisance for oil production. You know, they flare it off.
right, but they've got all the strictly models and all. Oil companies must have a bunch of this preliminary data we're asking for. Right, so why isn't BP here? They've got a big push of that.
Well, first of all, you're saying, why aren't they?
They are.
Yeah,
Yeah.
yeah,
Okay.
yeah. There's a lot of people in this space that if you got any experience in exploration, unless you're trying to get investors, you play it pretty close to your chest. I mean, back like some of the drill core samples, you know, I had an old professor told me that they would be given drill cores that had nothing to do with the project to leave around the site. That's how, you know. Now, with that being said, there's a ton of people running into this at once. What NextEnergy is just saying, there has to be a more thoughtful approach, because that simple graphic that I started the discussion with, that's the level of education. I think some people that are very excited about it for good reasons, mind you, but we need to develop that. And to your point on why aren't oil companies? Well, to me, that's phase one. Taking a look at all the old logs again. In fact, there's people at this university that I think are doing that.
Remember, they are very much demand driven, right? Because that's where their profit margin goes from.
Yeah. Yeah. And when they were drilling all those holes, okay, there was 3 billion people on the planet. All they needed was oil. I mean, everybody remember where oil started at on the planet?
That's
Well,
Yeah, Pennsylvania. a lot of people go Texas, Saudi Arabia, it's Pennsylvania. And they thought, well, where else could it be? That's, right now, we got a couple spots on the planet where we know that you can get it out of the ground at volume. So the question becomes, how many more are there like that? Because we really haven't been looking. So to me, phase 1 and phase 2 are kind of in that ballpark. But to me, this is the outline of the key players, government clearly, drilling rights, mining rights, academia research, this group. And this is something I think that's important. Bring in the people that have done this before, all the natural gas and oil people, because the wisdom of 1,000 dry holes is hard to beat. Okay. It's nice if every hole you drilled in the ground produced, but that's not the way it works. And that's even with very good geophysics in that. So, codes and standards, which we're going to hit in a little bit. And then, hydrogen city. Anything that needs hydrogen, you put it close to the well, or one of these brilliant minds here at Michigan State comes up with a way to store and transport it in a thermal neutral environment at atmospheric pressure so that we can put it in a conformable tank. Small ass. Small ass. Oh, energy density similar to gasoline or diesel, by the way. So if you guys could get that figured out like in the next couple of weeks, that'd be awesome.
Good.
So remember, it's going to be thermodynamically neutral, right? Close to it. All right. All right. You done? So I think this takes us into the
I'll
real
jump
work.
in now. Okay. So I'm going to talk about a kind of specific project that NextEnergy is supporting. We work with a group of industry partners that originally started with 6, Air Liquide, Hyundai, now go back to the other slide real quick. Nikola, Shell, and Toyota. So we do have some industry partners involved in this. Nikola obviously doesn't exist anymore. And then NREL is a Danish company and they rebranded. So Cavendish is the name of the group now. So this group formed back in 2019 with the goal of developing 70 MPa hydrogen heavy duty vehicle hardware, which we will show you on the next slide. Be able to refuel Class 8 truck at 10 kilograms per mile. So really try to get it more comparable to a diesel experience right now. So the group was, when the group formed in 2019, none of these components existed. So they put out an RFP, partnered with a couple of organizations to try to develop, actually do the engineering work to develop and test these components. And since then, it's already 2025, which is crazy, almost 2026. So over the past 6 years, have had success in getting prototype components, done some baseline validation testing, and then partnered with the National Renewable Energy Lab in Golden, Colorado to actually put these on their heavy duty dispensing system and see what it would look like to actually flow at those high rates. Okay, now you can go to the next slide. So very specifically, what we are supporting is, and to really oversimplify this, you can compare a hydrogen refueling station to a gas station dispenser. We're supporting the breakaway device, which in case you drove off, it would separate the hose itself, and then the nozzle and the receptacle. So those 4 components of the larger system that are necessary to fuel a vehicle. There are a lot of organizations, well, yes and no. There's really not that many, but there are a number of organizations that are trying to develop these components. All of them are international, so a couple of teams or companies in Japan, and then some in Europe that are developing the breakaway nozzle receptacle and then the hose components. So we worked throughout the 6 years with all of those various suppliers in various ways. So after developing and testing, doing some baseline testing on these components, we partnered with the National Renewable Energy Lab in Golden, Colorado to do a cooperative research agreement with them. And the goal of this cooperative research agreement was to help, again, further validate these components themselves, but then also to impact the codes and standards associated with all of these components and everything that goes into refueling components. So this was a DOE funded project, partnered with also, well, these were in this circle over here, those are the 6 organizations that NextEnergy sort of manages this group for them. And then we brought Chevron into it, and then our National Lab as well, and then a couple of the standards organizations. So the goal was, we provided the hardware, which are the photos kind of in the bottom corner there, some examples of the hardware, hoses, and the different connectors, and sent them to NREL, and they did a bunch of testing on these. They also had their analysis team do like TEO and TEA analysis as well, or TCO, sorry, total cost of ownership. And then all of the data generated from this then fed into the international ISO standards that are related to all these components. So focused on a couple things, I'll show you on another slide. The station itself, so NREL is the first place in the world that we are aware of that can flow hydrogen at these fast rates. So really the best place to test the components. Fueling protocols, so how fueling actually happens. So that's another thing that the group and this research is helping to inform, is how are the protocols being written. The hardware itself, which I've talked about, which was the original and primary focus of the industry group partners, was getting that hardware developed so it can be tested. And then the last step is the communications. So as you're fueling, what communications are happening between the vehicle and the dispensing system to make sure it's a safe fueling event. So tested all of those things, and there are codes and standards related to every single one of those that were impacted. Which next slide. So this is these pictures are kind of fun, but this is NREL's heavy duty hydrogen fast flow research facility. Don't try to say that fast at all, it's really hard to do. But they have a heavy duty vehicle simulator that they're able to, and they've kind of set it up as a circular system. So they have hydrogen in the system, they can fuel, and then they fill up their heavy duty vehicle simulator, and then they slowly recirculate that back so that they can do a number of iterations of fueling and not cost millions of dollars worth of hydrogen to do all their testing. This I put in here because I thought it may be interesting for the engineering team, but these are all like the tech capabilities of the station itself out in Colorado. So I borrowed this slide from the NREL team, but it's a public slide, so no worries there. So they have their heavy duty dispenser, heavy duty vehicle simulator, they have bulk gas storage, they have a cooling system, and then the gas management panel, and like I said, with the gas recirculation, so they're able to do multiple fueling events. So this station is, again, like I said, we believe, first of its kind, it's experimental, but there was really nowhere else that we're aware of in the world at this point that you can actually flow at these high speeds that are ultimate industry goal to get to. But right now, this is the only place, and we're aware of a project that's happening right now in Europe, a collaboration with a couple of different European entities that is standing up a refueling station, I think in the Netherlands, that should be online at the beginning of 2026. So this station had like a 2 to 3 year advantage over the one that's going live in Europe. So really grateful we got the opportunity to utilize this equipment and partner with it to test. Okay. Next slide.
And you're trying to get to like a 10-minute refueling
Yeah.
time for a Class 8 truck, which is comparable to what happens today, right?
Exactly. Yeah.
So that's about comparable with traditional gasoline fueling.
Yeah, exactly. And I think that's one of the drivers, right? Is that right now, if you were to refuel, they have, especially out in California, they have Class 8 trucks, hydrogen trucks on the road, but they're fueling 20 minutes, 30 minutes. They've got dual dispensers perhaps, or like dual nozzles so that they can try to fill faster. But the ultimate like goal for the industry would just be able to flow at 10 kilograms a minute off like as a standard, so that across the board the refuel for the vehicle would be somewhere around 10 minutes or less. Again, to make it more comparable to what exists right now. So the thought is like truly you can go run in, go to the bathroom, grab a snack, come out, your vehicle's full and you're back on the road versus waiting 20 or 30 minutes to fill up. What pressure is that what you asked? Seven.
In the vehicle or in the truck.
Yeah, 700 bar.
7 bar.
700. Yeah, 70 MPa.
Thank you.
Yes.
How much experience do they have? Do they have any read on reliability of these systems over time?
Read on the reliability. That is actually something that has been uncovered a little bit in this testing that we've done so far. For example, it's pretty well known throughout the industry that the compressor system is one of the least reliable parts of this dispenser, the overall dispensing system. And so there's definitely interest in like, how does this become more reliable, etc. So on the component side, we've had a lot of success without any leakages or really any failures on the components that our team was providing, but the overall system, it's still in the research stage. And so there's a lot of discoveries being made. There's an interest on the NREL side. They have a secondary campus that has a little bit more space and a little bit more, that has more space, and they're building a hydrogen generation. Can't remember all the details of it, but the idea that they have is that they could somehow find the funding and the partnerships to then create another like test bed where they can test all the other components of the system, not just it's easy to swap out these smaller components that we are bringing to the table in testing, but in the existing system right now, it's very hard to, for example, swap out a compressor or do some of the larger component testing for reliability. So there's interest in doing more of that because the reliability is still not to industry standard, I would say.
You mentioned no failures, but I think the more important metric would be mean time between failures.
That's
for
true.
these components. Do you have an idea of that? Do you have enough statistics, or you haven't operated long enough to have confidence?
Yeah, mean time between failures of the components. I'm just repeating in case the folks couldn't hear that question. So we are doing a fairly limited number of runs here, so we don't really have the statistics on that. But in the ISO standards, there are like very specific tests that are supposed to help generate like cycle life for the components. I think because these are prototype components, we set them at like 500 cycles or something before they would need to be swapped out. Again, just in collaboration with the manufacturers and knowing that they're prototype components and just to be overly cautious on the safety side of things. So we set the life cycle, I think, at something like 500, but the industry standard, if someone fact checks me, I might be wrong, but I'm like 80% confident that it's something like 15,000 cycles. So we have it like way low just for this.
Yeah, I would imagine that, I mean, so 500 cycles is less than a week of standard operation for a fueling station for large trucks. So you would imagine it's probably 3 days worth.
Exactly.
So that's way too fast of a tempo, right?
Yeah, exactly. So the one of the other challenges with the station as it exists, because it's experimental, is that they can't recirculate the gas very quickly. So they can only do like their capacity of their vehicle simulator, I think, is right around that 80 kilogram mark, which would again be what you would want on a Class 8 truck. And I think if I have it correct, they can actually only fully load that thing up one time a day. And then it takes a really long time to recirculate the gas back through their system to then run another test. So they're only able to even process like one true refueling event per day, which doesn't really truly simulate the real world at all, right?
And that's because of thermal considerations, or?
Yeah, it's some restrictions that they have on their both, I think, thermal and then like the correct. So I think that they have to It's something with how they store it. They store it at a different pressure in the vehicle simulator than they store it in their bulk storage. And so there's some like pressure differentiation that they have to like manage as well. And then the temperature. I don't remember all the details of why
no, that makes
it's
sense.
so slow to circulate, but it's a combination of those kinds of things. Yep. Shoot, that had inspired me to say something else, but it's gone out of my brain. If I think of it, I'll bring it back up. But I wanted to highlight as well, very cool, exciting thing is that this project actually did win an award from the DOE on the research that we did. So these are some of the engineers that are on site at DOE or at NREL that are working on this. And here is a picture of a heavy duty dispenser. We didn't really use this on our station or on our testing. But this was recognized in 2024 for this, because it was the first time we were able to actually hit that target of, it's kind of this, right in the middle of the bulk of this paragraph. I probably should have highlighted it here, but we were able to hit that 10 kilogram per minute fueling event using a fueling protocol, and using the components. And so I was able to actually truly do that full cycle simulation for the first time, using all these things. So everything came together in like a successful fueling event at the rates, targeted rates, hit the capacity of the machine. And again, use those protocols to be able to do that. So that was kind of the main goal of the first iteration of this. Right now we're in conversations with NREL. It's a little tricky with the government being shut down, but we're in conversations with NREL to continue this work and do additional testing on the components, but with even heavier focus on the protocols, the fueling protocols and the fueling communications, because all of those standards are currently under revision as well. I think you can go to the next slide. Yeah, and then these are just as a reference, all of the standards, the immediate standards that we're impacting through this work. So most of the work that we're doing is supporting the ISO organization and the National Standards Organization. So just for reference, I threw these all on here, but I don't know why I spelled geometry like that. That looks like a European spelling or just really poor spelling. But connector geometries. So there's an international standard for fueling at a rate up to and including 120 grams a second, which is kind of already existing. And then the work that we've been doing at NREL is this greater than 120 grams per second rate. So in here, there's all sorts of tests that are trying to simulate the real world. Like, what does it look like to fuel 4 trucks in a row? Does the nozzle freeze onto the receptacle? What does that look like? Right now, yes, it does. And so what are the mitigations that you need to put in place so that it doesn't freeze on and you don't get a truck driver who gets his crowbar out and tries to pry it up, right? Because that's actually what happens in the real world. If this guy's got to go somewhere and he can't get unattached from the dispenser. So all of those kinds of conversations and some of the testing is included in that, again, to try to get to what the life cycle of the components should actually be. Fueling hoses as well. So those are all the kind of components. There's a breakaway device that I didn't put on here because that standard is not currently being revised, but it's still impacted, obviously, because that's one of the components that we're developing. And then fueling protocols and advanced communications. So how are you actually fueling the vehicle? What is the system doing in order to fuel? And then how are the dispenser and the vehicle system communicating with each other? And what does that look like? So all of that is being impacted by the research that mostly NREL is doing, but we are supporting through the industry group that I work with. And like I said, we're in conversations with them to start like a second cooperative research agreement. Industry groups trying to put in some funding. We're hoping to get some funding from the DOE. I don't know what the status of that's going to be. And then with a focus on finalizing some tests here to make sure, again, we're doing that proper simulation for what does the real world look like. But then also focus on the fueling protocols and communications to help advance those documents that are currently being revised. So all of these are on kind of pretty aggressive timelines where the industry itself, like the partners that, like Toyota, for example, Shell, and others that are in part of the industry group, and many others that participate in the ISO organization, for these, they want these to be the standard like tomorrow, if possible, right? Especially if you're on the development side at any of these OEMs, you need to know what you're planning for, what you're designing for on your vehicle or on the dispenser side. So there's trying to push really aggressive timelines on all these, but also standards and research take a long time. So the most recent version of the top one on this list was published in August of this year, but all of these are most likely going to be published sometime in 2026 or 2027 when they become the latest version of the option standard. I think that might have been all my slides. I don't remember. Yeah, that was all my slides. Yeah. So I think from there we can just broadly open it to questions for either of us or any of the work that we're doing.
Well, let's thank the speaker. Questions?
What do you think is the next killer app? Where's a real sweet spot for hydrogen application?
Well, I think two. I think marine applications. And I also think anywhere where battery weight is problematic. And so I don't know how much you guys participate in the aerospace side of things, but eVTOLs are kind of going ballistic right now. And you know, they're battery electric. They have limited range because they're doing the same dance between mass and functionality. But I think those two can come to the table. And by the way, the cheaper you make hydrogen and the less problematic and less expensive it is to store it, enable many more business cases.
What do you think of between the geological hydrogen and also the hydrogen from the green hydrogen from electrochemical processing from water? How these two things in market or commercialization perspectives?
Well, the thing that's attractive about geological hydrogen is that you'd be getting it out of the ground real cheap. Like the number you keep seeing is $1 a kilogram, even though, you know, Africa is doing a little bit less. The challenge when you do green hydrogen and you're using renewables and you're doing electrolysis is that you're taking and you're compressing it as a gas. You're taking all these hits, right? So you know you can compress it. That's 50%. Okay. Electrolysis, that's another 25. You know, so all of a sudden the math doesn't look favorable, except it's everywhere. We just got to get better at doing it. And by the way, electrolysis has improved dramatically over the last 10 years. Dramatically. As have batteries. Midwestern accent there, batteries. Batteries, for instance. You know, when we did the first electric vehicle in California, the battery cost was like around $900 a kilowatt hour. Okay. When I left Stellantis, sure it's probably not secret now, but you know, we were getting down into the 120 per kilowatt hour. And I know that for storage applications, non-automotive, I can guarantee they're quoting well below 100 now. So we need that to happen with hydrogen. All right. Is anybody with the MOFs here? Wow. Okay. So the MOF challenge for you guys is, can you get to something that's a little more thermodynamically neutral and can get out of its own way in the tank? That's historically what's been the challenge with those. But you know, the idea that there might be a material that allows you to improve the energy density of your device, I think there's a lot of merit. When I was at Stellantis, we were looking at a material that was nearly thermodynamically neutral and would find 4 hydrogens per site. But they had trouble replicating it. And so whether it's geologic hydrogen, MOFs or COFs or you know, the latest new battery, solid state battery technology, all these things tend to work well at small scale, but when you put them in system level, you got to start worrying about heating and cooling and keeping. When somebody asks me, good question on the hydrogen, but you know, what should I focus on first? I always tell them go stationary apps. Mobile apps are just such a son of a gun to live in. You know, -40, +80, shock, vibration, FMVSS, and all that. It's not that we can't figure it out. We have. There's cars. I drove on one today. Got all the way here. You know, but it get the first dollar, the easy dollar, and then work on improving it, which is kind of, you know, the 10 kilogram a minute thing was like the holy grail when I was dealing with this at 350 bar. You know, now they're doing it. And you go, well, you got to do this and that, and we got a lot more challenges. But once you do it, you figure it out, right? I mean, we used to sell minivans to Waymo, and it looked like a Homer mobile, you know, it had all this junk taped to the outside of it. And but you know, all that equipment's got nice and small. We just got to figure out how to do it with hydrogen.
Here, I forgot there's supposed to.
Oh, yeah.
I think you're pretty clear on here without it.
Oh, you can?
Yep.
Yeah, I think I'm fine with it. So from an environmental protection perspective, for the geological hydrogen production, what kind of liquid or solid waste do you all expecting to generate during this kind of production? Is it similar to oil and gas industries where you have hydraulic fracturing, where you will be producing a lot of produced water that needs to be managed eventually?
I would imagine that drilling the hole would involve all the same concerns that we have. I just don't see why it would be any different. Now, once you have the hole drilled and you develop the well and set your casing and whatever it takes to do for hydrogen as opposed to natural gas, you know, the central processing facilities, what would those look like? It's probably parts of it will be the same, but I'm guessing we're going to have something different because, for instance, if you're lucky enough to have helium, you're going to want to sort that out. So you're going to have, you know, a processing site that'll have the same kind of environmental, probably permitting and you know, constraints on it. But when you drill a deep hole, you typically use water and mud to get the cuttings out, right? Yeah.
I'm asking because like produced water management in the oil and gas industry has been somewhat challenging, and sometimes you will have to use deep well injection to manage the solid waste generated, and that can be, from an environmental protection perspective, can be a ticking bomb if we inject them back into the ground, and just in case if there are like any earthquake, seismic, or those kind of events that may release those pollutants back into the groundwater or maybe into surface water.
Well, you know, when you design a waste injection well, you have to take into account your seismic classification of the area you're in. And I will tell you that, at least on the stuff I've seen, that if you have a seismic event big enough to get down to that, you probably got several other issues that you're going to be dealing with a little bit more priority, but not to diminish in it. That's why I put codes and standards up there. I mean, it's not just about the end user and making sure that they're safe and you got the right cycling for the components and the systems. It's also, you know, what is geologic hydrogen going to mean? Well, it'll mean, you know, a potential, you know, exploration boom, whether it's geophysics out in the field or, you know, drilling more holes. But it's something we know how to do. Might have to go a little deeper this time.
So as a follow-up to that, obviously, we're not going to be using the garden hose that you showed in your AI generated example. But
You sure?
I'm pretty sure.
Okay. All right. All right.
No pressure. But in any case, so I'm imagining somewhat different from hydrocarbon production. The porosity of the rock and the storage scale of the rock may be different. So the fracking fluid nature might be different and in fact somewhat more simple in the case of hydrogen production. Is that right? Is that the right way to think of it?
I think that's a way to think of it. That's kind of what I'm thinking. I'm thinking it's going to be a lot more diffuse. I think maybe, who knows, you might not need to frack.
But larger caverns and so on.
Well, cavern is kind of a wishful,
Yeah.
you
Well, it's a glacial formation. That's why we're.
yeah. Well, or I keep hearing, the salt mines in Detroit, but salts are a great impermeable barrier for a reservoir, a great capstone. In the Mali Africa example, it's a dye base, which is a granitic material. They had these intrusions come in and kind of provide a nice little cap to these areas. And we have those, in the Keweenaw dye base and Marquette area too. So to your point, we're in step 1 and 2 of that one slide. And to me, that's where academia and universities can really step in, because all those models that are built for natural gas, they're probably a good, boilerplate to start from, but they're going to have to get tweaked. And there's people doing that today at these sites that we cite, but that's just the beginning.
Has there been any published work on that? On how different is the modeling for hydrogen than hydrocarbons?
So I was trying to find that actually. I'm sure that some of the work being done in Kansas and some of these other places, that they're tweaking the models as we speak. I haven't seen anybody saying, here's a natural gas field. If we put hydrogen in it, it would be modeled this way. Because the challenge with geology is the heterogeneity of the material, right? And you interpolate between 2 drill holes and you hope that you got your best guess in there. And so you're always doing some fancy math in between those, trying to get that. But porosity and permeability, which are related but are completely separate from each other, that's what's going to govern gas moving from one area to another. But it's hydrogen, not natural gas. So, and at that depth, even the fluids are going to behave a little bit.
Lauren, your work is focused on, or has been focused on, standards for the refueling hardware. We also looked at standards for site operations, weight measures, types of protocols, or emergency response type protocols, or just anything related to a refueling site for itself.
So personally, no, and the work that my group is doing is like very narrowly focused on the components and the refueling like protocols there. But those standards do exist. So I have broad awareness because I'm involved in the ISO, it's like technical committee focused on hydrogen, and they do some annual like updates across all of the standards that they have. And that includes like all of that as well, and hydrogen storage and transportation. And so there's like a whole list of 60 plus different related standards that all fall under that TC 197 hydrogen focus group within ISO. But unfortunately, my personal experience and the focus of our group is really just on the ones that I was highlighting. So I don't know a lot about the other ones. I just am aware that they exist. Yeah.
Yeah. Look at like ICC, International Code Council, and NFPA, which if you look at like the state of Michigan fueling for petroleum in that I think was actually modified a little bit for hydrogen at one point, because I sat on it committee once. So take a look at the fueling protocol, but I think NFPA and ICC is where they powered, took a lot of that language from, because they always adopt with additions and amendments, right? So then within the continental United States, or just the United States period, you have 4,500 authorities having jurisdiction. And so ideally you would hope that they'd all be the same, and they generally reference the same text, but the individual municipality or whatever may have a different addition or amendment to it.
What kind of funding opportunities or collaboration with professors? I think from your company's perspective or in general in industry, and you also mentioned several of the funding has been cut or being redirected. So to us, how the collaborations between industry or your company with the professors, and do you have any perspective?
Well, it's interesting because the Detroit ecosystem that I showed you up front, they are working towards a publicly funded model with private investment in addition to any kind of government help that they can get. And I think at least near term, that's what you're going to see a lot of industry sponsored stuff. I mean, we'll see. You know, these are pendulum swings. I've watched it go back and forth a couple of times, but I think you're going to see where the use case and the business case are aligned. You're going to be looking more at industry funded efforts, at least what I'm seeing
Yeah, I would agree.
near term.
Even the project I'm talking about where we're looking to expand, the industry has put in funding for that. And so as if all else fails, we are able to do an industry funded project at NREL still, at least at current state. It would just be supplemented and we'd be able to do more if we could get DOE to also infuse some funding into the project, right? Which is how the first one worked and was so successful. So we're hopeful that that's the case, but okay, we don't know what the federal budget's going to look like. So
I'm on one of the science committees, advisory committees for DOE, and I can assure you they're not talking to us
yeah,
for a long time. And they're in fact disbanding the advisory committees now, and they're going to coalesce into a single committee, which is going to be more politically focused and less scientifically focused. So none of that is great news. So given that scenario, and given NextEnergy's position, is there an opportunity for it to serve as sort of a broker between industry and academia in terms of matchmaking, developing teams that can do the research that normally the federal government would have done the matchmaking on? Is there a rising opportunity?
Well, it's not just an opportunity, it's something we've done.
So do you plan to escalate that given the current situation?
Well, you know, be viable, we'll have to expand, you know, the industrial funding aspect of it. But you also have to remember that not everything's just federally funded. You have state level,
Sure, for sure.
You know, so a lot of things depend on, you know, how all that works out. But to me, that's kind of the lesson learned from the last time hydrogen went into hibernation, right? When we had the hydrogen hangover last time, it's like, oh, you know, fuel cell vehicles maybe in a different country, but not here and all that. But, you know, what happened was in the forklift area, it was just a better business case because they didn't want to buy they wanted zero emissions because they're indoors. Okay. Not because of, I mean, environmental, but because of indoor air quality. And the cost of two battery electrics, because you needed one while the other one was charging, the fuel cell won. Okay. So I think that's the challenge. Now, if your question is what about fundamental research, I think that's going to be a tough one for a while.
Well, for a university like Michigan State, we're probably more shifted, especially in engineering, more shifted towards applied research.
Yeah.
So that's, I think, it's great to our advantage.
I would concur with that assessment. I think look, there's strength in doing basic raw research, and because nothing gets to the level of commercialization until you've done that, right? But if you have an idea, go through what it takes to commercialize it, see where you're at in that process. You know, NASA has their little thing where, you know, are you 7 or 8 or whatever it is, and you know, you can take a look at that, but, you know, if you take a look at Lauren's work with codes and standards, I've had this conversation with so many startups, and there's a big sense of optimism on what it takes to get something out for sale in the public or even in pilot phase. And codes and standards is a big wall. Storage materials. I mean, CSA, you know, all the work you're doing with the international codes and everything else. It's, you know, you got to look at that pathway. How close are you to that? Because that's when you can go knock on industry store.
And part of the reality there is a lot of the codes and standards are aimed at a different parameter regime. And are maybe not always appropriate for new parameter regimes, and therefore new standards development is going to turn out to be important because you just can't extrapolate the existing standards.
That's 100% true, and I think you're going to see that with hydrogen in a lot of different areas.
And I think universities are also a good place, and you know, we can combine forces with, you know, demo places like ACM in this area. So those are things that I think are available in Michigan that not everybody has. So,
yeah, agreed.
So I'm just looking through that work you guys are making parts the same time, and then it seems like you're building, participating, making arrangements and doing standards. So I'm still trying to figure out exactly what are you guys going for? Like, what are you best in the world at? What's your mission statement? Does the industry just outsource the research departments to you with us for projects, and you take it over and then enact it, or what is your operating philosophy?
Well, to, you know, put the statement I had up front, if you have a program, and we call ourselves honest brokers, right? And you don't want a specific player in an industry to manage the project, and you want somebody that can be an honest broker for the results. We help get technology out in the hands of communities so that they can actually use it, or with an industrial partner, or looking at something that's pre-competitive, like you know, heavy duty truck refueling, and we manage those programs for people.
So Jason, a little interpretation. So honest broker here doesn't mean that others are dishonest. What it means is a company may be motivated for their technology to be adopted in the standard, and having a neutral party to arbiter that between multiple interests is crucial.
I will tell you, the first time I did codes and standards work, I thought I was being punished. I don't know. Yeah.
Sometimes.
Yeah. But because I thought I was going to get bored, terribly bored. And it can be a little bit monotonous, but I will tell you this: the most lively, emotional, nearly fisticuff fights, and I'm not kidding, people standing up, bumping chests, was at codes and standards meetings. And because, you know, I'm company X with a certain IP, and I want to, you can't make it the standard, or you got to give away your IP. That's one thing. They don't make somebody's IP a standard, but you don't want your IP boxed out of the standard. So, and we've seen it before. I saw it with fueling communications and all that. So it can be very interesting. Even the station regulations were like that.
It's like the roadhouse of technology.
Yeah.
Do you think CE is going to live with the ISO standards, or are they going to want to write their own?
You know,
The ones that I'm working on, they just have a reference back to the ISO standard.
Okay.
Right now. That doesn't mean that they wouldn't change in the future, but at least on the ones that I had on the list, most of them, the SAE standard that is relevant, they just say reference ISO.
yeah, at the end of the day, nobody has the bandwidth to do all this. Right. And that now could you end up with an addition or amendment to an existing standard,
right,
or a North American application? Sure. anybody that's done codes and standards work, there's a very old joke, five countries got together and said it's silly that we all have a different standard to do this. Let's get together and we'll come up with one standard. And they get together and then there's 6 standards. And that joke isn't too far off sometimes.
So, sorry, I was missing most of the discussion because my class was having one big beautiful meeting today. So for the class, I do have a question. So I wonder, like, your thoughts or opinions about the respective future of hydrogen power and battery power in the vehicles. Maybe you have already discussed this, but if you could provide any information, that's much appreciated, especially given that Tesla has announced that they're ready to produce semi in large numbers next year.
Yeah, I didn't exactly talk about any Class 8 like battery powered vehicles, but most of everyone I can't remember when you stepped in, but I'm helping to support an industry group that consists on the vehicle side of Toyota, Hyundai, and then it used to be Nikola, but obviously it doesn't exist anymore. So on the vehicle side, it's mostly just those 2 on the OEMs, and then there's 3 others that are more on the hydrogen production and delivery side. But both of those organizations are doing both, right? They're doing the battery powered and the hydrogen powered. And there's I have the bias because I'm like in the weeds on hydrogen side, right? But everyone that I'm working with is really hopeful and driving towards, hey, there will be a future for hydrogen powered Class 8 trucks and above, right? And that's why all this work is going into that. But there's a reality where they're both going to exist, right? I don't think, and we sort of mentioned this earlier, probably before you came in, just broadly across the industry. I think it's not a which one will win, it's how many of both, right? Where both solutions are going to be relevant. I think hydrogen has some advantages, especially when you get the refueling time down and the cost of hydrogen down, right? You can go a lot distance wise on the hydrogen, but right now it's very expensive, and there's like one place in the world you can fuel at the rate we want to fuel at, and it's a research station, so it's not realistic right now. Versus the battery, it's much more realistic as a current right now solution. You just can't go quite as far distance as you could with like a diesel truck.
So you focus that answer on heavy trucks.
Yeah.
But it seems like a lot, and maybe even simpler problem is both marine and rail. And MSU actually have a big rail center which is focused on business supply chain aspects of rail, but is starting to leak over into the technology aspects for exactly these kinds of reasons. And you can imagine in a diesel electric tractor of a train, it's not crazy to think it's pretty easy just to swap the power plant and leave the electric tractor drive train in place, and you're good to go. So it's actually a pretty simple proposition.
Yeah.
With a lot of storage capacity if you wanted to store whatever is powering your power plant.
Yeah, absolutely.
A serial hybrid application is kind of makes sense. That to your point though, I don't have it in this presentation, but we used to have a kind of like a size vehicle versus battery versus hydrogen. And to Lauren's point, when we started to talk, it's it's not going to be a this or that conversation. Both will probably live there. But as you get bigger into the vehicles with current battery technology, the battery starts cannibalizing the functionality of the vehicle. So from a mobility point of view, hydrogen tends to live better in larger vehicles. It's not that it can't go in smaller vehicles, it just makes more sense. The use case is more favorable. But with regard to long term, both these technologies will be living side by side.
Thank you.
for better, like I said, that most of the ions in the battery just sit there, they just keep the crystal structure open. Right, and only a small percentage of liquid goes in and out. Whereas in a fuel like hydrogen, whatever, every single bond of that you will part getting energy out. So the energy density of when it's fuel based, it's really much higher than battery. So
Yeah, you know, at the end of the day, we're trying to trick electrons to hang out by each other, and they don't want to. And you know, it's cheaper to move electrons than molecules, but you know, at the end of the day, you're going to need both because there's more people using more energy. And certain use cases are just going to favor batteries. Certain use cases are going to favor hydrogen, whether it's ice or fuel cells. You know, and as engineers and scientists, you know, our challenge will be to, you know, do that in a safe and economical way. You know, we can do it pretty safely now. We're just trying to get the economics down. You know, we got to pump hydrogen up to 10,000 psi. You know, that costs money, takes equipment, capital investment, you know, cycle time. If you could fill a battery as fast as you could fill a hydrogen tank, you know, that'd be great.
I want to be respectful of time. I think we're at that time, and I know we've already lost some people due to classes, either that or they objected to standards, but
Yeah.
I think it was class.
Yeah.
So I think let's thank the speakers again.